this is lecture number 4 of structure of atom. In the last lecture, we have done electromagnetic wave theory and electromagnetic spectrum, characteristics of electromagnetic radiations, all that we have done. Now, what are the limitations of electromagnetic wave theory? So, electromagnetic wave theory, it was this electromagnetic wave theory electromagnetic wave theory, it was successful in explaining properties like interference, diffraction. Now, what is interference and what is diffraction? See, we have this wave, another wave. Now, when these two waves interfere and crest over the crest, trough over the trough, then it is like this: crest part, trough part, crest part, trough part. So, crest part will increase, trough part also increase, and this is called constructive interference. So, this constructive interference can be explained by wave nature of light. Even destructive interference like crest over the trough and trough over the crest. So, it is like this. Okay, so this part, that is crest over trough or trough over crest. So, crest and trough both will decrease, and that is called destructive interference. One is constructive interference, other is destructive interference, and both these interference are explained by wave nature of light. And what is diffraction? Diffraction is bending of light at the edges. Bending of light. That is called diffraction. This interference and diffraction, they are explained by the wave nature of light. But this wave nature of light could not explain the phenomenon of black body radiation, the photoelectric effect, the variation of heat capacity of solids as a function of temperature, and the line spectra of atoms with respect to hydrogen. That the one which we are going to explain today, the black body radiation, photoelectric effect, and spectra of it. This means spectra of hydrogen, means line spectra of atoms with respect to hydrogen, that we are going to do today. Okay, these are the limitations of the wave nature of or electromagnetic wave theory or wave nature of light. So first is black body radiation. So first, what is black body? So black body is actually any ideal body. It is an ideal body which can emit or absorb all the frequencies, comes in its way. That is called a black body. Means it is like this, that there is some hole, a small orifice, and it is circular, and there is a wedge here. So when a light enter in it, there is a multiple reflection, and therefore whole light gets absorbed in the body. It will not emit, it will not go back due to multiple reflections. means any radiation which comes gets absorbed in it, and after the absorption all radiations are emitted, means any body, that's why it is called ideal body. Why ideal? Because such body cannot exist which can absorb all types of radiations and emit all types of frequencies or radiations. That's why it is called an ideal body which can absorb all the frequencies and emits all the frequencies. So such body is called black body, and those radiations are called black body radiation. So according to, if you say the exact frequency distribution of the emitted radiation from a black body, it depends on its temperature. See, this is intensity, and this one is, here it is wavelength. So when we plot a graph, so when we plot a graph between intensity and wavelength, so see, as the wavelength decreases, see, as the wavelength decreases, intensity increases, reaches a maximum, and then on further decrease in wavelength, it will decrease. First it increases with decrease in wavelength and then reaches a maximum, first increase and then decrease. And if we increase the temperature, there is more intense. If we increase the temperature, the intensity maxima is at higher end and at the same time at a lower wavelength. You can see maxima at temperature T1 is at this wavelength, and intensity maxima at temperature T2. T2 is greater than T1. See, this is at temperature T2 and this one is at temperature T1. So intensity distribution is more and maxima is at a lower wavelength as we increase the temperature. But first it reaches maximum and then decrease. So this phenomena could not be explained by the wave nature of the radiation. Why is it so? Because according to the electromagnetic wave theory, whenever energy is absorbed, though it has low wavelength or high frequency, it continues to be absorbed. And when it absorption takes place, at the end there is infinite energy. So any body with infinite energy cannot exist. Means according to electromagnetic theory, this energy is added up. Whatever energy goes closer to the, is whatever energy that is absorbed, that body go on absorbing the energy of any frequency. So as energy is going to be added up at the time when high energy radiations are absorbed, the energy of the body goes on increasing, and ultimately it is to be infinite. And energy to be infinite, that is not possible. So that is according to electromagnetic wave theory. But this black body radiation, see, when wavelength is large, wavelength large means, if wavelength is large, what it means? Energy is low. Wavelength large means frequency low, because frequency and wavelength are related. Frequency into wavelength is c, that is speed of light. So as lambda is large, wave frequency is low. So at higher wavelength and low frequency, intensity is increasing. But when wavelength is very low, at very low wavelength or means high frequency, the body starts emitting the energy. This indicates this. See the graph. First it goes up. See, first it goes up, reaches a maximum, and at lower wavelength means higher frequency, it starts decreasing. Intensity starts decreasing. That means first it absorb, reaches maximum, and then it start re-emitting. So this re-emitting emission of radiation that is not explained by electromagnetic wave theory. So this is the limitation of electromagnetic wave theory, that it could not explain the black body radiation. Okay. See, at a given temperature, intensity of radiation emitted increases with the decrease of wavelength, reaches a maximum, first emitted radiation, intensity of radiation emitted increases with decrease of wavelength, reaches a maximum value at a given wavelength, and then start decreasing with further decrease of wavelength. So this phenomena is not explained by electromagnetic wave theory. So did you understand what is black body? Yes, beta. It is an ideal body which can absorb all types of frequencies and which can emit. It is an ideal body which can emit all types of radiations and which can absorb all types of radiations. It can emit all types of radiations. It can absorb all types of radiations. It is as simple as that. Simple definition. Ideal body is the black body is the one. It is an ideal body which can absorb all types of frequencies and it can re-emit all types of frequencies. That's it. Yes, beta. Okay. Now, Planck's quantum theory. So, what is Planck's quantum theory? So, according to Planck's quantum theory, say to explain this phenomenon of black body radiation and at the same time photoelectric effect, that we are going to do in the next section. Max Planck in 1900 put forward a theory, and this theory is known as black body. This theory is known as Planck's quantum theory, and this theory then was further extended by Einstein in 1905. So main points are the radiant energy, the energy which is emitted or absorbed by any body is in the form of small packets. In the form of small packets, and each such packets of energy is called a quantum. What I said, the radiant energy, it is emitted or absorbed, not continuously. It is not emitted or absorbed continuously, not continuously. Okay, but it is emitted or absorbed discontinuously. We can write discontinuously. Okay, instead of not continuously, we can write discontinuously in the form of small packets of energy, and that small packet, each such small packet is called quantum. Each such small packet is called quantum. But I said the radiant energy, it is emitted or absorbed discontinuously. It is not continuously absorbed or emitted. It is emitted or absorbed discontinuously in the form of small packets. And that's such a small packet is called quantum. And in case of light, this quantum is called photon. It is called photon. In case of light, okay, in case of light, these energy packets are called photons. And energy of each quantum, it is directly proportional to frequency of radiation. That means E is proportional to nu. Energy is proportional to nu. And what is nu? Nu is the frequency of radiation. And it is also known as E equal to h nu. Or nu is related to lambda in this form, C upon lambda. So you can write E equal to h nu or E equal to hc over lambda. And what is h here? Okay, here h is called, what is h? H is, yes, it is a constant called or known as Planck's constant. And its value is fixed, that is 6.626 into 10 raised to power minus 34 joule second. Now, the total amount of energy emitted or absorbed by a body, it is some whole number multiple or integral multiple of quantum. So third point we can add the total amount of energy emitted or absorbed by a body is some whole number or integral multiple of quantum. That is E equal to nh nu. E equal to nh nu. And what is n? N is an integer, that is 1, 2, 3, 4, etc. And energy associated with the Avogadro's number, of quanta is called Einstein of energy. So this is the relation between E and nu, E and lambda. Means E equal to h nu, that is the energy of one quantum or energy of one photon, and E equal to nh nu, that is the total energy emitted or absorbed by a body. N is 1, 2, 3, 4. It can emit or absorb not continuously but discontinuously in the form of small packets, either 1 h nu, 2 h nu, 3 h nu, 4 h nu, and so on. And if we talk about energy associated with 1 mole of quanta, that is called 1 Einstein of energy. That's it. Okay, so now we have relation C. Two relations we have done. First, we have lambda into nu equal to C, that we have done before. And second, we have done E equal to h nu or E equal to hc over lambda. Okay, now come to the next part. It is photoelectric effect. Now this photoelectric effect, this experiment was done by Hertz in 1887. What he discovered? He discovered when a beam of light, say this is the light, a beam of light of certain frequency, when it strikes to the metal surface, this metal surface, then electrons are emitted. Electrons are emitted from the metal surface, and this phenomenon is called photoelectric effect. See, photon light, in case of light, that small packet of energy is called photon. So this photon strike the metal surface and get the electron. That's why these two terms, photo means photon and electric means electron. So ejection or removal of electron with the help of photon, that is called photoelectric effect. See, the equipment for studying the photoelectric effect: light of a particular frequency, it strikes a clean metal surface inside a vacuum chamber. Electrons are ejected from the metal and are counted by a detector that measures their kinetic energy. See, here energy of the incident photon, if it is taken as E naught, let us say energy of this incident photon is E. So this energy is utilized in two ways. What are those ways? First, energy, a small amount of energy or a minimum amount of energy is required to remove the electron from the metal surface, and that energy is called threshold energy. What is threshold energy? Minimum energy required to eject an electron from the metal surface. So that energy is called threshold energy or work function of the metal, or it is also known as binding energy of the metal. So in chemistry we use two terms only, threshold energy or work function. So this is E naught, denoted by E naught or W naught, threshold energy or work function of the metal. What do you mean by threshold energy? Minimum energy of radiation which is required to eject an electron, that is called threshold energy or work function. That is called threshold energy or work function. and E naught or W naught. Okay, so that means energy of incident photon is E. Out of E, E naught is used to eject the electron, to remove the electron. So the amount of energy which is remaining, that is converted into the kinetic energy of the electron. That means energy of the incident photon is utilized in two ways. First, a small part is used to remove the electron from the metal surface, and rest becomes its kinetic energy. Is you can write it like this: E equal to E naught plus kinetic energy, or E equal to W naught plus kinetic energy. Now, if m is the mass of the electron and v is velocity of the electron, then it becomes E equal to E naught plus half mv square. Or if frequency is nu, so E equal to h nu, and threshold frequency is at nu naught, say, and the minimum frequency of the radiation, if we write here minimum frequency which is required to eject an electron, that is called threshold frequency. Instead of energy, we write frequency only. And this is photoelectric equation. So what he observed, see, his observations are observations in photoelectric effect. First is only photons of light of certain minimum frequency, that is called threshold frequency. This is nu naught, not V naught. This is nu naught, that can cause the photoelectric effect. That means if frequency of the incident photon is greater than or equal to threshold frequency, only then photoelectric effect is observed. And this value of nu naught, that is value of the threshold frequency, it is different for different metals. Like if we have potassium, rubidium and cesium, then nu naught of potassium is greater than rubidium and it is greater than cesium, because cesium is large in size. As cesium is large in size, it is easier to remove electron from cesium rather than rubidium or potassium. Next part, kinetic energy of the electrons which are emitted, it is proportional to the frequency of the striking photon and is independent of their intensity. See what it means. We have written E equal to E naught plus kinetic energy. That implies kinetic energy is equal to E minus E naught. Now, E naught is fixed. So that means kinetic energy depends upon the energy of the incident photon. This is the energy of the incident photon. Or it depends upon the energy of the frequency of the incident photon. See, kinetic energy of the electron which are emitted is directly proportional to frequency of the striking photon. But there is no intensity involved. What is intensity? Number of photons striking the metal per second. In 1 second, how many photons strike the metal? Frequency or kinetic energy has no relation with intensity. So kinetic, if in frequency is same, all the photons can eject electron with the same kinetic energy. So as intensity increases, number of photons which eject increases. And one more thing, one photon can eject only one electron. That is very important. One photon can eject one electron, not more than that. One photon can eject only one electron. Then number of electrons that are ejected per second from the metal surface, they depend upon the intensity of the photon or radiation and not upon their frequency. There is no relation with the frequency, but there is a relation with the intensity. That means if we plot a graph let us plot a graph between kinetic energy and frequency. So let us plot a graph between kinetic energy and frequency. So if we plot a graph between kinetic energy and frequency, 1 second, wait. Okay. See, this is kinetic energy of photoelectron, and this is frequency. See, what was the relation? Kinetic energy equal to H common nu minus nu naught. So see, if nu is equal to nu is less than nu naught, then kinetic energy comes out to be negative, which has no sense because kinetic energy can never be negative because kinetic energy is half mv square. Mass can never be negative and there is a sphere of velocity, so that is also always positive. So kinetic energy should be positive. That means if nu is less than nu naught, no photoelectric effect is observed. Okay, if nu is equal to nu naught, then kinetic energy is 0, and if nu is greater than nu naught, kinetic energy is positive. That means kinetic energy then increases. Means up to nu equal to nu naught, there is no kinetic energy of the photoelectron. Reason being, no electron can be ejected because minimum frequency of the radiation required to eject an electron is nu naught. So after that, it will increase like this. So this is the relation between kinetic energy and frequency. Now, what is the relation between kinetic energy of photoelectron and intensity? It remains same. And third is relation between number of photoelectrons versus intensity. So as intensity increases, because I said you one photon can eject one electron. I told you just now. So as intensity increases, means number of photons striking the metal per second increases, number of photoelectrons increases. So there is a linear relation. Okay. So in this way, we can have these three graphs. First, kinetic energy and frequency. So there is a direct relation. Intensity and number of photoelectrons, direct relation, but kinetic energy and intensity has no relation at all. Okay. Next. Now, explanation of photoelectric effect. So say the observations that of experiment observed by Hertz could not explain, but Einstein gave this explanation, and as Einstein gave the explanation, he got the Nobel Prize for that. So Einstein 1905 was able to give an explanation for different points of the photoelectric effect using Planck's quantum theory. First thing, photoelectrons are ejected only when the incident light has a certain minimum frequency that is called threshold frequency. Means if radiation incident light has frequency equal to or greater than threshold frequency, only then photoelectrons are ejected. Second thing, if the frequency of the incident radiation is more than the threshold frequency, the excess energy is imparted to the electron as the kinetic energy. Just now I have told you the same thing, that one part of the energy of the incident photon is used to eject the electron, and that energy required is called E naught, and rest of the energy is converted into its kinetic energy. So kinetic energy of the ejected electron, kinetic energy of the ejected electron, energy of the emitted electron. Leave it. Okay, next is on increasing the intensity of the light. On increasing the intensity of light, more electrons are ejected, but the energy of the electrons are not altered. Energy remains same. This part is that kinetic energy of the ejected electron, that is called photoelectron, is proportional to the frequency of incident photon. So this is all about photoelectric effect. Yes, beta, did you understand photoelectric effect? Simply, photoelectric effect is ejection of electron with the help of a photon, and energy of the incident photon is used in two ways. First part, one part of the incident energy of the incident photon is used to eject the electron, and minimum energy required to eject an electron, that is called threshold energy, and remaining energy, the energy of the incident photon, with excess energy, that is converted into the kinetic energy of the photoelectron. Okay, next part is dual behavior of electromagnetic radiation. So see, this black body radiation, this photoelectric effect, that is explained by the particle nature of the light, because one photon can eject one electron. First thing. Second, energy is emitted or absorbed discontinuously in the form of packets, that is in the form of photon. So that is explained by the particle nature of light. Black body radiation, photoelectric effect. Diffraction and interference, they are explained by the wave nature of the light. That means electromagnetic radiation has dual nature. They can behave as wave as well as particle, depending upon the phenomenon. So say, from the study of the behavior of light, scientists came to the conclusion that light and other electromagnetic radiations have dual nature. These are wave nature as well as particle nature. So whenever radiation interacts with the matter, it displays particle-like properties in contrast to the wave-like properties like interference and diffraction, which it exhibits when it propagates. So some microscopic particles like electrons also exhibit this wave particle duality. So you know, when subatomic particles like electron is moving, it moves like a wave. But you know, electron has mass. So as it has mass, That means it can show particle nature, but it can also behave as a wave. That's why it can show wave nature. So electromagnetic radiations has dual nature. Particle also, microscopic particles also have dual nature. Now come to the spectrum. So what is spectrum actually? Spectrum means when a ray of white light, white light composed of whole waveguide, right? Dispersion of light you may have learned in lower classes. So when a ray of light, it is passed through a prism. Let us say this is a prism. So when a ray of light is passed through a prism, the wave with a shorter wavelength, it deviates more than the one with a longer wavelength. So see, it is like this. Means the wave with shorter wavelength like violet, then indigo, then blue, green, yellow, red, orange or red, right? So this whole waveguide is formed. Okay. So the wave with shorter wavelength, it bends more than the one with a longer wavelength. And this ordinary white light consists of waves with all the wavelengths in the visible range. The array of white light is spread out into a series of colored bands, and that is called spectrum. This is called a spectrum. The light of red color, which has longest wavelength, it is deviated the least, and violet light, which has shortest wavelength, is deviated the most. Okay, so in this way a whole waveguide is formed, and that is called spectrum. And say these lines are continuous, they are merging into each other, and that's why it is called continuous spectrum. What we call it as continuous spectrum. So first of all, you may have this dispersion of light in lower class even. Okay, when white light, it is passed through a prism, it undergoes dispersion. Okay, means the light, even sunlight, this is actually white light is white light means, let us say this is sunlight. Now, continuous spectrum. So when a ray of white light is analyzed by passing through a prism, it is observed that it splits up into 7 different white bands of colors from violet to red, like rainbow, and these colors are so continuous that each of them merges into the next. Hence the spectrum is called continuous spectrum. So this is actually the continuous spectrum, right? Now emission spectrum. Emission spectra, it is noticed when radiations emitted from a source, they are passed through a prism and then received on the photographic plate. So radiations can be emitted in a number of ways, like from sun, that is a simple source. even uh, electric bulb, glowing electric bulb that can emit light even by passing electric discharge through a gas at low pressure and by heating a substance to high temperature. You know, when we heat a substance at high temperature, it emits first red color, then blue color. It's like that. Okay. So these are the source of emission spectrum. Even when we burn a lit gas stove, so that emit light. So line spectrum, that is one type of emission spectrum. Actually, when the vapors of some volatile substance, they are allowed to fall on the flame or a Bunsen burner. Okay, this is Bunsen burner, let us say. So when vapors of some volatile substance, they are allowed to fall on the flame or Bunsen burner and then analyzed with the help of spectroscope. Then, you know, if we have sodium, that is also called flame test. Like see, sodium give yellow light of two wavelengths, 5890 angstrom and 5896 angstrom. So some specific color lines appear on the photographic plate and which are different for different substances. For example, sodium or its salts, they emit a yellow light. Potassium or its salt give out violet light. So that is they mean sodium, potassium, calcium. Calcium give brick red color, barium light green, apple green. See, sodium give yellow, potassium violet, calcium brick red, barium apple green. Okay, so these are the color given by these ions and their salts. Okay, so that is what we call them flame test. So we can detect them by flame test. Means their salt is heated in flame, and if they emit yellow light, that means it is a sodium salt. If it emit violet light, it is a potassium salt. If it gives brick red color, that is a calcium salt. If it gives apple green color, that is a barium. It is the salt of barium. So that is called line spectrum, and it is for elements. Now, line spectrum of hydrogen. So how do we get this line spectrum of hydrogen? When electric discharge, it is passed through hydrogen gas, which is enclosed in a discharge tube under low pressure, and the emitted light is analyzed by a spectroscope. The spectrum consists of a large number of lines which are grouped into different series, and the complete spectrum is known as hydrogen spectrum. So on the basis of experimental observations, Johannes Rydberg, they noted all series of lines in the hydrogen spectrum. They could be described by the following expression. And what is the expression? Expression is 1 upon lambda. 1 upon lambda is equal to, wait, Okay, so 1 upon lambda, that is equal to nu var, that is wave number, RH 1 upon n1 square minus 1 upon n2 square. So this is called Rydberg equation. What we call it? Rydberg formula. See, this equation is known as Rydberg formula. Okay, and this RH is called Rydberg constant, and its value is 1.09677 into 10 raised to power 5 per centimeter, or 1.09677 into 10 raised per 7 per meter. Okay, this n1 and n2 are actually integers, and in this case n2 is always greater than n1. n2 is always greater than n1. This is called Rydberg formula, and if n1 is taken as 2, see, if n1 is equal to 2, the formula is known as Balmer formula, because this Balmer formula is in the visible region. So say nu bar equal to 1 upon lambda equal to RH 1 upon 2 square, means 1 upon 4, or we can say 1 upon 2 square minus 1 upon n2 square. That is called Balmer formula. And for any atom other than hydrogen, but that should be one electron species, like lithium 1 plus, beryllium 2 plus, boron, lithium 1 plus, beryllium, lithium 2 plus, beryllium 3 plus, boron 4 plus. So see, lithium has 3 electrons, 2 are lost, so 1 electron system. Beryllium 4 electrons, 3 electrons are lost, so 1 electron system. Boron 5 electrons, 4 electrons are lost, so 1 electron system. So nu bar equal to 1 upon lambda equal to RH 1 upon n1 square minus 1 upon n2 square into z square. Then it becomes like this. This Balmer formula, this Balmer formula as well as this Rydberg formula, they are for hydrogen atom only. So say this is some white light source. Now we are talking about absorption spectrum. Okay, earlier it was emission spectrum, but first let us explain emission spectrum only. We will come to this part later on. Okay, see, this one. Now hydrogen atom we have, right? We have hydrogen atom. You know, hydrogen atom has 1 electron, N1, N2, N3, 4, 5, 6, 7, 8. So any electron, when electric discharge is passed, electron from the ground state, this is ground state, right? In hydrogen, electron is in the first shell. Electron is in the first shell. So as electron is in the first shell, so when electric discharge is passed or it is heated, means it absorbs energy. So electron can excite to, it can go, these are all excited states. So electron can be excited to second level, third level, fourth level, fifth level, sixth level, seventh level, eighth level, or infinite level, because there are infinite number of levels possible for any atom. So any electron from in the hydrogen atom, if it fall from higher level to first level, say this one, from higher level to first, any higher level to first level, N1 equal to 1 and N2 is anything greater than 2. Sorry, N1 is 1 and N2 is greater than 1. Greater than 1 means 2, 3, 4, 5, 6, so on infinity. So all the lines are known as, are under the heading of Lyman series. All those spectral lines are taken as Lyman series and it is in the ultraviolet region. It is in the ultraviolet region. And see the difference between N1 and N equal to 1 and N equal to 2 is maximum. N equal to 2 and 3 is less. N equal to 3 and 4 still less. So it goes on decreasing and at the end it becomes continue. Means energy difference is maximum between first and second level. Then second and third, fourth and fifth. Okay, any line comes to the 2 from any higher level. N1 equal to 2 and N2 is greater than 2. So that is called Balmer series and that is in the visible region. So any line from higher level to 3, any electron comes from the higher level to the third level, that is called Paschen series and it is in the infrared region. So there is whole table like this in the NCRT. See, what is Lyman series? Spectral lines for atomic hydrogen. Lyman series in which N1 is 1, N1 is 1 and N2 is 2, 3, 4, so on. And what is the region? It is in the ultraviolet region. Balmer series, any electron when fall at the second level from any higher level, 3, 4, 5, 6, so on. Paschen series, when electrons fall to the third level from any higher level, 4, 3, 5, and that is in the infrared, all in the infrared. UV energy of UV is greater than visible, which in turn greater than IR. Bracket series 4 from any higher level, 5, 6, so on. E fund 5 from any higher level. Then next is Humphrey series and one is 6 from any higher, that is again infrared. So this is the series of spectral lines from any higher level. So you can draw it like this, that let us say this is the nucleus, this is the first level, second level, third level, fourth level, fifth level, sixth level, and so on. Let us say this is seventh level. Okay. So if electron come to, this is 1, 2, 3, 4, 5, 6, 7. So any electron from higher level to first, any higher level to what is the name of this series? Tell me. If electron comes from any higher level to first level, what is the name of the series? Lyman series, right? If electron comes to the second level from any higher level, then what is the name of the series? Balmer series, right? And if it comes to the third level from any higher level, then what is the name of the series? Paschen series. If it comes to the fourth level from any higher level, fourth level from any higher level, that is called bracket series. To the fifth level from any higher level, that is called P fund series. Okay, these are the energy levels. Okay, shells. Now there is a hydrogen. So in the container, in the discharge tube, there are millions of hydrogen atoms. In few of them, electron is excited to seventh level. In few of them, electron is excited to sixth level. In few of them, it is excited to fifth level, fourth level, third level, second level. So in this way, these are the series, and Lyman series lies in the ultraviolet region. Balmer series in the visible region. That's why it is most important. And rest of them are in the IR region. So this is all emission spectrum, because electron is excited, means first it is excited in the discharge tube, and then electron comes back to the ground state, comes back to the lower energy state, from higher to lower. So energy is overall released. See, this is higher level, this is lower level. So electron is excited, means coming back to lower level. So energy is released equal to this energy difference between the two levels. That's why it is an emission spectrum. This is called emission spectrum of hydrogen atom. Now see this, atomic emission and atomic absorption. See, if this is excited sample, it is passed through the slit, then directly to the prism, and this is the detector film, and which detect that these are the lights coming from the sample. So this is called emission spectrum, because in emission spectrum there is nothing absorbing medium, no absorbing medium in between. But see, this is the white light source, and in between if there is an absorbing sample, so this absorbing sample absorbs some of the radiations. So when this sample now coming out of this absorbing sample, pass through the prism, some of the lines are missing. Some of the lines are missing, and that is called absorption. That is always discontinuous. The emission spectrum may be continuous or discontinuous, but absorption spectrum is always discontinuous. See, when white light is passed through unexcited atomic hydrogen and then through a slit and prism, the transmitted light is lacking in intensity at the same wavelengths as are emitted in the line spectrum, photographic negative of the emission spectrum. See, like if it is sodium samples, okay, so sodium sample emit yellow light, and same is the case that sodium sample absorb yellow light. When it is absorbed, it emit the same light. Absorbing and absorption spectrum and emission spectrum, they are complementary to each other. See, in this excited sample, this light is there, this one. But when this excited sample is unexcited and it is placed here, then that energy is absorbed, and here there is no energy. It is black colored because what? Okay, means when a substance is in ground state. Ground state means low energy state. That means it is unexcited sample. Means at low energy state. That is unexcited sample. Okay. Now second is excited sample. Excited sample means in higher energy state. Like there is hydrogen atom. In hydrogen atom, electron should be where the electron should be. At the first level, electron should be at the first shell, in the first shell. Right, beta? But if instead of in the first shell, electron is in the second shell. Instead of first shell, it is in the second shell. That means it is excited sample. And this is hydrogen in the ground state, means it is unexcited state. Okay, the most stable state. Okay, so absorption and emission spectrum, the difference is only that in absorption spectrum there is some absorbing medium in between the prism and the source. Okay, see this one. If there is absorbing medium between the source and the prism, that is called absorption spectrum. The spectrum observed on the film, photographic film or detector, that is called absorption spectrum. And if it is between the source and prism, there is no such medium, absorbing medium, the spectrum observed is called emission spectrum. What is this? This is simply slit which makes a fine beam. Okay, this is slit, but this is the absorbing medium which absorbs some of the light. If source before passing through the prism is passed through absorbing medium which absorbs some of the light, then that is called absorption spectrum. So say now we have three formulas. First was lambda into nu equal to c, that is lambda equal to c upon nu, or c, sorry, or nu equal to C over lambda. Second, 1 upon lambda equal to nu bar, that is wave number. Third, E equal to h nu hc over lambda or hc into nu bar. And fourth is 1 upon lambda equal to nu bar equal to RH 1 upon n1 square minus 1 upon n2 square. That is the wave number or 1 upon lambda of the emission line of hydrogen atom. N1 and N2 are shell numbers. RH is Rydberg constant. Its value is 1.09677 into 10 raised to power 5 per centimeter, or 1.09677 into 10 raised to power 7 per meter. H is 6.626 into 10 raised to power minus 34 joule second. So keep these formulas ready. Oh, one more, that E equal to E naught plus kinetic energy, photoelectric equation, that is also called photoelectric equation, or H nu equal to H nu naught plus half mv square, or half mv square equal to H nu minus nu naught. Nu is at frequency of the incident photon, nu naught is frequency of minimum frequency of the light or radiation required to eject an electron, that is threshold frequency, right? So keep in mind these 5 formulas. We will do some of the questions next time. Okay, uh, uh, just call me afterwards. Actually, I'm not able to hear you properly. Okay. Okay. Don't worry, I will. Okay, thank you. So that's all for the day. Thank you so much to all of you to be with me throughout this journey. See, we are doing the NCRT exercise, NCRT theory, NCRT concept, NCRT in text questions, NCRT examples, NCRT exercise questions, and after that we will do JEE and NEET questions of the same chapter. So be with me, support my channel. It is all free of cost. So support my free education drive and share with your friends and all those who need my help. I will definitely help you to score better in your board exam, in your class exam, in your competitive exam. So I want my community to grow. More and more people will know my channel so that they will be benefited. So for that, I request all of you to share my channel with all your near and dear ones whom you care, and in your community as well, so that it is a chain. So continue this chain, don't break it. And I want my channel to grow, like we have 1 million subscribers within few years, or even within within this year, so that we have a wide variety of students who can ask me to make a video on this topic, that topic, and In this way, I will help all of you globally. That's my aim. Support me, and thank you all. Support me till date and supporting my channel. Thank you so much from the all heart, and my best wishes are always with you. You will grow, you will have knowledge, content more than I have. That is my wish. Thanks for watching. Have a nice day. Bye bye.